In Verilog, we can control the time. So at the beginning of the file, we specify the time scale. So we have a comma, a backward comma there, and time scale in 1 nanosecond and 1 picosecond. So we specify two numbers here. Between those numbers, we have slash there. The first number, 1 nanosecond, means the time unit to represent the time, meaning so this delay, when you specify like assign pound 1, y equal x, this pound is time delay. So time 1 nanosecond delay is passed, and then we do the actual assignment. So this is for the 1 nanosecond logic delay. What about the 1 picosecond? 1 picosecond means the internal simulation time step. It re-evaluate the value and check the events. Internally, it has the 1 picosecond simulation resolution. So you have to don't be confused with the 1 nanosecond and 1 picosecond. You can put it like a 10 nanosecond and let's say 100 femtosecond, etc. like that, or 100 picosecond. Right? You can change the time scale and the resolutions. Okay. But what you have to remember is that any delay we specified like this will not be actually synthesized. There is no way for we can actually accurately synthesize this kind of a delay. So even though you specify like this and put this code into CAD tool, it will just evaluate like just buffer. This buffer delay is only determined by the size of this buffer size, and output loading capacitance. This capacitance is coming from either wire loading, routing delay, routing capacitance, and also output the gate input parasitic capacitance will determine the actual delay, and also there's the resistance also involved in the wire line. So all these factors will determine the delay from input to the next stage input, right? From here to there, delay will be determined by calculating all these. The tool cannot guarantee this can be 1 nanosecond. This kind of description is only for a behavioral simulation purpose. Right? So you just want to check your behavior, some values before actually you synthesize this statement. You want to check and behavior, right? In that case, you want to model the delay sometimes. In that case, you use this property. So do not try to use that delay as do not assume that such a delay will be the final delay after synthesis. Okay. In each Verilog, let's look in more detail and how the simulation actually how the simulator interpret the Verilog time. So we have specified the simulation resolution. Every simulation resolution, for example, if we put like a time scale 1 nanosecond slash in 1 picosecond, then every 1 picosecond, time 0 is let's say 0, and time 1 is 1 picosecond after that time 0 and another time. You keep calculating all these events at any time step, simulation time step. It evaluate right hand first. It had 4 different time allocation. Q1 inside the Q1 process and Q2 process, Q3 and Q4. In Q1, it executes the evaluate right hand side of the all non-blocking assignment and right side, and they evaluate this and change left hand side of the all blocking assignment, right? Evaluate right hand side and they change left hand side for all continuous assignment, right? Because continuous assignment, you need to update immediately, right? So that's why the blocking and continuous assignment, they're evaluated in this Q1 and evaluate input, and they change the output of all primitives and evaluate print out all the display and write function, right? Here for the non-blocking assignment, for Q1 time, only we evaluate right hand side, right, all non-blocking assignment. We are not assigning at that time. So once all the non-blocking assignment is evaluated in Q1, then in Q2 actually we change left hand side, meaning we actual assignment happened. So variable is updated and in the Q2 times, right? You will see the difference how those blocking assignment and non-blocking assignments performed inside the Verilog file. Okay. In Q3 we do some like a monitor and strobe functions executed. This is for the debugging purposes, and some kind of call PLI function, some synchronization, internal tool related synchronization function executed, and Q4 also another PLI synchronize, RO synchronizing. I'm not sure what are those, but there's something that for the tool to wrap up or clean up things in each time, right? So this is done. So in time 1 we are doing those things repeated, right? So we see it here from the blocking assignment versus non-blocking assignment. Those are evaluated in different time slot, right? You need to see the difference. There are two hardware delay methods. So hardware has two primary propagation delay method. One is inertial delay and the other one is transport delay. For example, if you specify the buffer with a 10 nanosecond propagation delay, this buffer delay will be 10 nanosecond you specify, and then if you give in like the pulse, like input activity, so this first activity change happened, but only after 10 nanosecond, let's say 5 nanosecond, another activity happened, right? Even we haven't delayed that to 10 nanosecond yet, but such kind of activity is ignored. Any value after this will be ignored, right? In this implementation, in this way is implemented by the inertial delay. But in some case, you want to have a transport delay, having like this kind of glitch like a pulse within, let's say this is 10 nano, this is a 5 nano. You want to delay this behavior with a 10 nanosecond propagation delay. So in that case, if you implement that with the transport delay, the output waveform will be same as the input, but the output is delayed by 10 nanosecond. This is key difference between inertial delay implementation and transport delay implementation. As I mentioned before, this kind of delay specification is nothing to do with actual hardware. I mean, you cannot synthesize this behavior, but this kind of behavior is only for your own simulation purpose, your behavioral operation checking. You want to see the behavior, what happened with this kind of inertial delay, what happened with the transport delay. So you want to verify your block, right, with these difference. So you have to know the delay model that we are doing is whether inertial delay or transport delay. Between those two, the output waveforms are totally different. What you want, what would be the practical in circuit? So, well, if your circuit buffer is fast enough, any small glitch will pass through like this, like a transport delay. But if your buffer output rise time is very slow, then this kind of short glitch will be filtered out in actually. So actual situation in hardware, both can be happening, right? So you have to be aware of those cases, right? So the inertial delay is a model device with a finite switching speed, right? If any less switching, since this is finite, if the input is moving so fast, right, then it's just filtering out, right? If the rise time is, so buffer delay is 1 nanosecond here, but if you assume that rise time is 10 nanosecond as well, then the output will not present at the output, right? But if your delay buffer has a near infinite switching speed, infinite very fast rise and fall time, then you will see the glitch, right? So we have learned that for logic definition or logic for combinational logic implementation, there are two different assignment is there. One is blocking assignment, the other one is non-blocking assignment. For those two cases, we are like assuming there's no delay. So for the same input, it just comes out same as the input, right? As I mentioned before, so for the combination logic, it would be preferred to describe that in blocking statement, right? For combination logic. So we will more focus on that. So for non-blocking such kind of delay, we will see for non-blocking assignment, we use that in flip-flop description only, right? So let's say for blocking assignment, the delay we can specify like at the input, let's say 5 nanosecond delay and the assignment like this. So this is kind of a 5 nanosecond delayed evaluation. But for the delay, if you put a pound 5 nanosecond, then this is the delayed assignment, right? So what would be different, right? What would be different? So this line evaluated, we go into this line whenever input changes, right? So whenever input changes here at this moment, we go into this line and see the 5 nanosecond delay, right? So we wait for 5 nanosecond, and then we do evaluate. This input is now going to O3. So this value goes out to the output, right? Now, if the input is again to change to low, another 5 nanosecond later, right? This value, input value assigned to output, right? Again, so here we see the activity here. 5 nanosecond delay, 35. After 35 nanosecond delay, at that moment, we see the input. The input is 0. Here, another 5 nanosecond delay. at this active, but before actually we are, you see, actually we delay while we are wait for the activity, wait for 5 nanoseconds. Another input event happens. So this is a delayed assignment is ignored, and we evaluate again this falling edge again. We look at the falling edge again in 5 nanosecond delay. So in this kind of a situation, we were at this rising edge. We were trying to assign this input at 5 nanosecond. We are trying to wait, but before actually we get to the 5 nanosecond later, we are seeing another edge. So now we ignore the previous assignment condition and we evaluate this and wait for 5 nanosecond. And again, another thing happened, another edge happened. Now finally this one, the last edge. So this at 5 nanosecond later, we are seeing this value and assign that to 1, right? So this exactly follows the inertial delay cases, right? So we specify the 5 nanosecond delay here. If there's input activity happen within this 5 nanosecond window, then such kind of a operation is ignored, right? So we are getting like this kind of inertial delay. Okay. For non-blocking delay assignment, we put it like a delay before the input, before the input signal here. So you look at the comparison here, right? This is inertial delay. For non-blocking delay assignment, whenever input changes, you go into here, then input is delayed by the 5, and then actual assignment happens. So input is just delayed by 5 nanosecond and assigned. For here, special case, input we go into this always statement, and input is delayed by 5 nanoseconds, and we do that assignment. So we are this kind of assignment thing is delayed and then happen in the the Q2 times in the previous the example, the time allocation. So all those events are all executed, right? So it becomes like a transport delay, right? Okay, so this will not happen if you just first delay. If you specify that delay at the first, then this is a delayed evaluation. We are evaluating this one 5 nanosecond delay. So anything is a event happen, and even after so let's say within that 5 nanosecond period, another activity coming in, then those are ignored. So the output will be same as the inertial delay thing, right? So those are the same output. Okay. So for the previous lecture, we have learned that in the flip-flop sequential logic description, if you use a blocking statement like that, so input goes to y1 and y1 goes to y2. All these evaluation happen immediately, right? Actual assignment happen immediately. So y1 and y2 must be the same. So if the input comes in, same input comes in to the two flip-flops, this is equivalent to single flip-flop taking input, and this one y1 and y2, same as like that. So if you use non-blocking assignment here, then evaluation happen first, and then actual assignment will be happen in the last state, like a Q2 state, right? Q1 time we evaluate on the right hand side, and Q2 times actual assignment happen, right? So we have two different flip-flop having different y1 and y2. For this kind of thing, for clock comes in, for the clock and data like that, the output will be totally different, right? So most of the behavior we are thinking is this description, right? This description is what we really want in the actual hardware. So you must remember this kind of a non-blocking assignment, and also you have to imagine, you must be able to draw this kind of circuit, right? Once you look at this code, you must be able to draw this the output, okay, the code. This is very important for describing the flip-flop and also the combination logic, okay. In the flip-flop sequential logic description, if you put the delay at the front like this, it means 5 nanosecond delay and then assignment. Delayed assign delay. So actual 5 nanosecond later, this blocking statement will be executed, and then another 5 nanosecond later, blocking statement is evaluated. So it looks like there's a delay on the clock path, right? So if this is the case, then what we assume for the flip-flop sequential logic operation will be violated. So we don't want to specify like that. And also for the non-blocking statement as well, if you put a delay at the front, there should be equivalent to that will be equivalent to the delay on the clock path. So that is also not what we want, right? We should not use that kind of evaluation. So what we really want to model is sometimes clock to Q delay. If the input comes in and an output comes out with a certain delay, the output just comes out. There's just certain clock CTQ delay there. So if you want to model this kind of CTQ delay, you never use those kind of a description. For flip-flop operation, we never use blocking statement like this. If you use like a blocking statement and put the delay on here, first line executed, even though the first line, the pound 5, represent the clock to Q delay properly, but the next line evaluated 5 nanosecond later. So there will be equivalent, that will be equivalent to having another 5 nanosecond delay on the clock path. For the non-blocking assignment, if you put the pound sign here, those right-hand side statement will be evaluated at the same time. So all these, and then assignment happen. So this properly model the clock to Q delay of the flip-flop. So we must use those kind of representation if you want to model the clock to Q delay. So when a rising edge comes in, actually we sample this, and then 5 nanosecond later the output comes out again. So for the Y2 also, we sample the Y1 and the 5 nanosecond later it goes up, right? So this is a proper way of representing the clock to Q delay. So never use those, right? So you have to remember this. So what you have to remember is that for sequential logic assignment, we use the delayed assignment. For use the non-blocking assignment, right? This example also visualizes the potential issue if you use the blocking statement inside the sequential logic, combination logic, like a flip-flop description. For example, so this kind of assignment, non-blocking, the blocking assignment, this one evaluation and assignment happen in Q1 time of each time step, right? This one also evaluated in Q1 times. So without any delay description here, all these two separate always statements evaluate the same time. So input input in updated to y1 at the rising edge, but the y2 also update the y1 to look at the y1 and to reflect the y2. But all these events are happening at the same time, right? So we cannot distinguish this flip-flop operation. So output will be kind of what we cannot expect. So this is not the proper operation of the shift registers. So this is just you are putting the race condition, right? But on the other hand, for the non-blocking assignment like this, actual assignment evaluation happen in Q1 times, right? And then Q2 times actual assignment happen, right? So two different separate time the assignment happen. So even though there's no delay description, clock to Q delay description in here, potentially there is a delta delay inside, like a Q1 to Q2 different time slot, right? So the behavior properly capture the flip-flop operation. So output behaves like a flip-flop. So you in the sequential logic assignment, you must use a non-blocking statement, right? Blocking statement. This is the must, right? You have to remember this is very important. To reflect the clock to Q delay, you may use 5 nanosecond in front of the assignment, but those for separate always statement, these 5 nanosecond delay will be representing the delay on the clock path. This is not what we really want. We don't want to describe like this. This doesn't show the proper operation. If you really want to make things work, you can put the delay a different way. For 5 nanosecond clock to Q delay representation, if you use blocking statement here, you must use 5 nanosecond inside here. This will properly model the clock to Q delay. Without this 5 nanosecond, things will not work properly. So if you want to use blocking statement like this in separate the separate lines, you can use this. But in some cases you are adding like a y3 and y4. All these different statements will be added later while you are implementing more complicated circuit. You may end up having lots of a flip-flop implemented. In that case, you're having like this kind of a delay here. You cannot manage your code. So this is not recommended. Never use like this. You use always like this, right? 5 nanosecond in front of the input assignment. So this is the use the non-blocking assignment. So this is the proper way of modeling the clock to Q delay. Okay. So even though the blocking statement and 5 nanosecond delay, like in this description, properly model like the output like this, don't use this. We want to use this non-blocking assignment. Okay. So this is the rule of thumb for behavioral description. For combination logic design, you use the blocking assignment by default. Important. For sequential logic, you use the non-blocking assignment if there's no delay associated. If you want to put some delay, like a clock to Q delay, then put the delay in front here of the input variable here. In combination logic, if you want to model the delay, so inertial delay model, you use pound A equal B. For transport delay model, A non-blocking statement pound B. This is very this kind of thing is it might be tricky. So you as a rule of thumb, we don't want to use non-blocking description inside the combination logic. But if you really want to model the transport delay in your code, you have to use like this statement. Okay, this but this kind of delay things will not be properly synthesized, right? The delay will be, all delay will be ignored, right? So this kind of delay description is only for simulation purpose, not physical. This will not be handled by the CAD. Only for simulation, it will show you the waveform according to the delay description. Okay. For the synthesizable RTL description, we will use this kind of a non-blocking assignment for combination logic, and then blocking assignment. For some time in your code, you want to model the clock to Q delay here. This is for visualization purpose. This will not be actually, this delay will not be synthesized, right? This is only for verification, and we will not, those kind of delay will not, in the combination logic, will not be synthesized. It will just ignored by the tool, right? Those kind of delay will be ignored. Those description will be for the only simulation purpose. Okay, so far we just finished the Verilog. So I hope you enjoyed your course, and I hope you have a great success in describing Verilog on your career and research. Thank you.